Hi, here is a video on the topic of API 650 storage tank 1-foot method equation. But before that, we need to build some concepts related to shell thickness calculations. So storage tanks are often compared to tin cans mainly due to their thickness by diameter ratio. In fact, a storage tank is more fragile than a soda can, and if you compare their T by D ratios, the soda can T by D ratio is typically 4 to 5 times that of storage tanks. So care must be taken for loads acting on a storage tank, as these tank failures can pose significant risk due to the large quantities of often hazardous fluids stored inside. Now, a storage tank undergoes a lot of forces and loads, and as a result, various types of stresses are developed. We have listed here some of the main loads and stresses experienced by a storage tank. That is, for forces or loads, we can have hydrostatic head due to fluid stored inside, gas and vapor pressure inside tank, which is at the top of the liquid column, external loads on nozzle, live and dead loads can be weight of the component, vacuum or snow loads, etc. These forces alone or in combination can produce stresses in a tank material and components. Few main types of stresses induced in a tank due to above-mentioned forces are listed here. Hoop or circumferential stress, axial compressive stress, vertical bending stress, and any other local stress. In the coming slides, we'll see how some of these forces act on a storage tank and induce stresses. For a storage tank, the hoop stress is mainly developed due to static head of the stored liquid, so the profile of the stress will be like shown here. And often for medium and larger diameter tanks, we can select lower thicknesses for plates on top shell courses, as the stress will be lower due to lower hydrostatic head on the top shell courses. API 650 tank have two methods for calculating tank shell thickness, namely 1-foot method and variable point design method. And a comparison between the two will be presented in the later slide. Well, actual hoop stress profile is not exactly a diagonal line, but more like the red curved line shown here, and as found experimentally, the maximum stress location at the bottom of each shell course is at a height of about 1 foot or 0.3 meter. Stress profile across a shell course may look like this, and as we can see, it peaks around 0.3 meter or approximately 1 foot. Hence, the method is given the name of 1-foot method. So as previously stated, API 650 standard provides two methods for shell thickness calculation, namely 1-foot method and variable point design method. And here is a brief summary of comparison between the two. So 1-foot method is applicable up to 61 meter diameter, that is 200 feet. Whereas variable point design method is recommended for larger tank above 61 meter diameter. And there are other selection criteria for variable point method given in the code. 1-foot method provides easy to use direct formulas for calculation, but variable point method is complex and iterative, and as part of the procedure, the first calculation is derived from the 1-foot method, and then on iteration is done to reach the final thickness. 1-foot method, it calculates maximum stress at 0.3 meter or 1 foot height above the bottom of each shell. And in variable point method, we calculate more exact location of stress in each shell. And thereby, calculated stress is conservative in 1-foot method than variable point design method. And the stress calculated as per variable point method is more close to your actual hoop stress. 1-foot method ignores shear force and resulting elastic deflection, whereas variable point method considers it. And 1-foot method, the tank diameter is often limited by maximum thickness criteria. But for variable point method, it permits larger diameter tank for the same maximum thickness. So we'll derive this 1-foot method equation in both units, that is SI or metric units and USCS or US customary unit. So we begin with Barlow's formula, that is thickness is equal to P times diameter upon twice of stress. And we'll use the same units that are given in the code itself, that is diameter is in meter, height in meter also. And as we have stated in the previous slide, height equal to h minus 0.3, or for USCS unit, height is equal to h minus 1 foot. So we'll just calculate height at a location of 0.3 meter of 1 foot above the bottom of the shell course. And as we know that pressure due to static head is equal to rho gh. Here rho is the density, g is the acceleration due to gravity, and h is the head of the liquid. We'll utilize the g, which is specific gravity of fluid, and we know that density of any liquid is equal to density of water into specific gravity g. So we'll put this in our formula. So our respective equations will become thickness equal to rho gh into d over 2 into s. Now after rearranging, we'll get thickness equal to g over t into rho h d over stress. Here, as we have mentioned, that h equal to h minus 0.3 for SI unit, density equal to density of water into specific gravity, and we know that density of water is 1000 kg per meter cube. Here T is in units of meter. For USCS unit, h equal to h minus 1, and density of water here is 1.94 slug per foot cube, and here thickness is in unit of inches. For USCS unit, G equal to 32.2 feet per second square, and for SI unit, the value of small g is 9.81. So putting this in formula, we'll get this equation, and after arranging it again, we get the following equation. You can notice here the thickness is still in meter for SI units, and it is in feet for USCS units. So again rearranging, and remember, we have converted the thickness from higher or bigger unit to a smaller unit. That is, for SI unit, we converted it from a meter to millimeter. So accordingly, 1000 will be multiplied with the equation, and that 1000 is cancelled with the density of the liquid. So we'll get this as both 1000s are cancelled. So we get this equation, and for USCS unit, we are converting it from thickness to inches. So it is multiplied by 12. That we take this 12 on the other side of the equation, and after rearranging, we'll get for SI unit in millimeter is 9 times diameter into h minus 0.3 into specific gravity over stress. And for USCS unit, thickness in inches equal to 2.6 times diameter into h minus 1 into specific gravity over stress. Now, after adding corrosion allowance, we'll get this final equation, which is thickness in millimeter is 4.9 times diameter h minus 0.3 into g over s plus corrosion allowance, and respectively for USCS unit, thickness in inches is 2.6 times diameter h minus 1 into g upon stress plus corrosion allowance. And as we can see, we can compare these equations. These are the equations provided by API 650 code for both units, that is SI unit and USCS unit. So we can see how we started from a simple Barlow's formula and we ended up with this API 650 code equation for 1-foot method in both units. And the equation provided in the previous slide is for design condition. So stress S is equal to now SD, which is stress at design condition. Now for hydro test condition or test condition, we have to ignore corrosion allowance because it's in new condition. There is no corrosion for hydro test, and because we are conducting the test with water, so gravity or specific gravity of the liquid is 1. So again we are arranging, G will cancel out from the equation and there is no corrosion allowance for hydro test. We'll get this equation of 4.9 times D H minus 0.3 over stress of T. Now this one is different from SD. SD is stress at design temperature and ST is equal to stress at test temperature. And similarly for USCS unit, thickness at test temperature is 2.6 times diameter into H minus 1 over ST. Now one thing to note from this equation is that there is no internal pressure or P terminology in both these design and test condition equation in both units. And if we compare it with codes, other codes like BS standard, in their thickness calculation, there is a term P or internal pressure above the column head in the equation. But API 650 ignores it due to very less value in comparison with static head. Hence, we don't see a pressure P term in API 650 standard equation in comparison to BS standard.